home. Today we're going to take a very close look at the chi-squared test, which is an interesting test for evaluating whether certain proportions come out as expected or anticipated. So first we're going to look at a fairly theoretical side of it, and then we're going to look at things fairly practically. The chi-squared test differs from a test for proportion equal to a fixed value in that it's capable of handling multiple proportions at a time. Nevertheless, it's really useful to look at the test for a proportion in order to give context for the chi-squared test. So we're going to begin here by looking at a test for the proportion. Now, in a typical test for a proportion, we don't usually have all of this notation, but it might be useful to understand the context of the chi-squared test. So let's imagine a typical test for a proportion in which we have n cases of a two-category variable. Maybe it's true, false, something else. We have observed counts, c hat 1 and c hat 2. These are not the observed proportions, but just the counts. Maybe there are 100 in this case and 200 in this case. We can calculate the observed proportions, p hat, which is c hat 1 over n, and q hat, which is c hat 2 over n. This is simply saying nothing more than you take the given counts and you divide by the total number, and that gives you the given proportions. These are the observed proportions, p hat and q hat. Q hat is the opposite proportion from p hat. If you calculated p hat, then 1 minus p hat would be q hat. Now, those proportions in any hypothesis test for the proportion are going to be compared against some sort of fixed comparison value, which we would write p, and then its opposite would be q. So we might have a null hypothesis lurking around, which tells us, hey, I expect that proportion should be exactly 50%, and then p would be exactly 50%. And C1 would be exactly half of n, and C2 would also, in that case, be exactly half of n. If we were comparing against a fixed value of 25%, then P would be 0.25, Q would be 0.75, C1 and C2 would be the counts anticipated, which might be 250 out of 1,000 and 750 out of 1,000, something like that. So let's look at the formulas for the standard error and the z-score, and then the square of that z-score. So whenever we're doing a hypothesis test for a proportion, we'll have to look at the standard error for that proportion, which is the square root of p times 1 minus p over n. And then we'll get a z-score out of that, the measured value p hat minus the anticipated value p divided by the standard error. And I've just plugged in the formula for the standard error here. So p times 1 minus p over n square root down there. Now, if we wanted to clear the square root, we could square both sides of this formula. That would give us a z squared here, a p hat minus p quantity squared here, and then the square root would go away in the bottom, and we would just get p times 1 minus p over the square root over n. Now, if we wanted to do some algebra with that, which I'm actually going to skip, but you can check this on your own, by plugging in the values c1 over n, c2 over n, c1 hat over n, c2 hat over n for p and p hat, by plugging in all of those values and simplifying, we could convert this formula for z squared to this peculiar formula here. So this is an alternate formula for z squared. And if you're running a simple hypothesis test for a proportion, you can, in theory, calculate z squared by using this formula and then take the square root to get the actual z-score. Now, I'm not recommending that you do that, but in theory, this is an alternate formula for not z, but the square of the z-score. Notice that it seems to depend on the measured value C1 hat and also on the measured value C2 hat. Now, these aren't truly two different measured values, you see, because if we are measuring n cases, then some of them are going to be counted by C1 hat, and the rest of them are going to be counted by C2 hat. So really, we always know that C2 hat is n minus C1 hat. So these aren't truly two different independent variables, but they kind of look it in this formula. So what we really have in this formula is only one true variable, C1 hat, and C2 hat is derived from it. But we have two terms in this, and it kind of looks like we have two variables. To record the fact that we really only have one free variable here, and that the other one, C2 hat, is actually a function of it, we say this has 1 degree of freedom in this formula. However, this is an interesting formula because it separates all the true cases and all the false cases. Or if we're doing some other two-category variable like male and female, all the male cases, all the female cases, right? Or good and bad, all the good cases, all the bad cases. So this is a computation that only involves one of those categories. And this is a second calculation that involves only the other category. So that's interesting. And that guides us as we move forward to a situation where there are more than two categories. This thing over here doesn't generalize nicely to three categories or four or five, but this thing is suggestive. What would you do if you had to have more than two categories? You would have an extra term in here for the counts, and it would be like C3 hat minus C3 quantity squared over C3. And that's exactly what we actually do when we're doing the chi-squared test. So the chi-squared test is a test which calculates the test statistic z-squared and calculates it this way. If we have many categories, not just two, not just true and false, not just good and bad, but many categories, A, B, C, D, whatever, then we'll have many different counts. We'll have some anticipated counts that come from a null hypothesis. That would be C1, C2, CK. And then we'll have some actually measured counts that come from the data. That would be C1 hat, C2 hat, all the way through the last C sub k hat. So what we do is we take this formula up here and we just generalize it to having many categories. We calculate the square of the difference and divide by the anticipated count, and then we add up all of those, and that gives us a new test statistic, which we call z-squared. And that test statistic has a chi-squared distribution with, we say, k minus 1 degrees of freedom. So up here, I argued that C2 hat is actually a function of C1 hat, and therefore it only has 1 degree of freedom, even though it has two terms. In general, we might have 10 terms, but it would have only 9 degrees of freedom, because the last term is really just the total count minus the others. So this is how the chi-squared test really works underneath the hood. We calculate these counts and we plug them into this formula, and then we get a statistic z-squared. Now, this formula has a sum of squares. And to understand it intuitively, you should think of it as analogous to a distance formula, which also has a sum of squares of differences in it. So the predicted counts are C1, C2 through CK. The measured counts are C1 hat, C2 hat through CK count, CK hat here. This sum of squares should remind you of the distance formula. And what it's really doing is it's calculating how far away are the measured counts from the anticipated, expected, predicted counts. If they are very far, then we get a big value of the test statistic, which tells us something weird is going on. If they are very close, then we'll get a small value of the test statistic. So in a way, this is just a fancy calculation of the distance between our expectations given by the counts CI and our actual measurements given by the counts CI hat. It's just calculating the distance between our expectations and our measurements, which is a good way of calculating a test statistic, right? Now, this test statistic ends up being distributed in a chi-squared way. This is not normally distributed. It has a completely different distribution. And it's worse than that. It's not that it has necessarily the chi-squared distribution, but it has one of many distributions, all of which are called chi-squared, one for each possible degree of freedom. So we've seen graphs of the normal distribution, which predict the anticipated values of the test statistic z. Let's have a look at the chi-squared distribution, which tells us what to expect of this z-squared thing. So let's look at this graph. So here I've got a whole bunch of code here, but this is just, the whole point of this code is to plot the chi-squared distribution. So you don't need to look through this and understand the code. Let's look at the picture. So this is the plot of the chi-squared distributions. The first thing you should notice is there's more than one. There's lots. There are 9 different distributions plotted here. And if I have more degrees of freedom, then we'll get even more. So that's a little disturbing. That means that whatever distribution we're using, we need to know how many degrees of freedom we have up front. Otherwise, we won't even know what distribution to compare against. So if we have 10 different categories, then we do something like this. We'll have 9 degrees of freedom. Then we have to pick the right graph, the one with 9 degrees of freedom, and compare our z-squared to that. So our z-squared value that we get here is going to be somewhere on this graph. And all we really need to do to perform the chi-squared test is identify the right graph first, maybe 9 degrees of freedom, find the z-squared value, and then calculate the right tail of that. This is not the normal curve. These are chi-squared distributions, not the normal distributions. And so we mustn't get confused. We have to compare the test statistic that we have now, which is this thing calculated as z-squared. We have to compare the test statistic we have to the appropriate distribution for that test statistic, which is this chi-squared distribution. Now, how do we do that? Well, there are several different ways to do that. And they all basically amount to how are we actually going to calculate that right tail area on this new crazy distribution and get a p-value. So how do we find the p-value? Well, one way, and the simplest way, if you are working within Colab or any interface to Python, is to use the scipystats chi2 CDF function, which actually directly calculates that right tail area. Actually, I lied. It directly calculates the left tail area, which is kind of unfortunate, but standard. I mean, it's the right thing to do, but it's inconvenient for us. This directly calculates the left tail area. So if you actually want the right tail area, you have to subtract from 1. So notice that, so into this function, stats.chi2.cdf, I have to plug in the test statistic, which in this case is the calculated value of z-squared. So whatever you got for that z-squared, it goes in here. But it takes a second argument. What is this? The second argument is the degrees of freedom. So if we have 3 degrees of freedom, if we have, for example, 4 categories, then we would have 3 degrees of freedom. Then we would plug in the degrees of freedom here, and we would plug in the calculated test statistic from there. We would plug it into this function, and we would get the left tail area, say like from here to the left, and then we would subtract from 1 because what we actually wanted was the right tail area. So that's, if you're working within Colab, that is absolutely the simplest way to get the right tail area, which calculates the p-value for the chi-squared test. Now, that's not the only way, and we're not always working within Colab, so I want to give you a few more options here. Another way to do this is to use an applet. There are numerous applets on the web. This one is kind of nice. We can plug in the degrees of freedom here, and then we can plug in the value of the test statistic here, and then it will simply calculate the right tail area, which is about 0.04601. Notice that agrees with the calculation here. So if we just use a simple chi-square distribution, the one advantage of this is that it actually plots something. It actually illustrates to us, this is the distribution that we're comparing to. This is the right tail area here, which is what we're actually calculating. And so we actually see a picture of what we're doing here. I want to point out here that when this page loaded, it did not show the graph. The reason it did not show the graph is because it shouldn't have, because depending on the degrees of freedom, it might have one graph, it might have another graph. It needs to know the degrees of freedom before it can choose the right graph. And if the degrees of freedom is different, then we'll get a different graph here. So whenever we're doing the chi-square distribution, we need to be sure that we're using the right distribution for our problem. And so we need to have the right number for the degrees of freedom. This DF here stands for degrees of freedom. It doesn't stand for data frame, so don't get confused with the standard notation for a data frame in Colab. So option 1 was we actually use this function, which you can copy from this workbook, which will be linked in the comments. Option 2 is we use some sort of online calculator, and that works just as well. Option 3, I'm including because it's the traditional way, but I'm also kind of calling it old school because it's a little bit old school. Option 3 is we use a table lookup. Before we had easy, convenient access to computers all the time, we had to have a way of calculating these, of finalizing these hypothesis tests without even the use of a computer. And so we have table lookups for these things. Now, these table lookups are a little bit complicated. This is an example of a chi-squared table. And so let me teach you briefly how to read this. First of all, this is the Python code that creates a chi-squared table. You don't need to worry about how I did that. You can, if you're going to be using a chi-squared table, you're not going to be building your own. You're going to be looking it up on the internet somewhere. I just wanted to make sure that I wasn't copying somebody else's work, so I made my own. So here's a chi-squared table. Now across the top, we actually, we don't, what we have here is the alpha value. And because alpha equals 0.05 is kind of standard, you should focus on this column here, alpha equals 0.05. This is the alpha value across the top. What we have across the side here, this is the number of degrees of freedom. So if we wanted to assess a hypothesis test for a chi-squared test and we got a test statistic of 8 with 3 degrees of freedom, what we would do is we would focus on this row with 3 degrees of freedom. And then we would read the alpha value here. And what do we look up? We look up 7.81. That's the value to beat. That's the value so that if your test statistic beats that, then you have statistical significance. So in this case, I would look up the degrees of freedom here, my alpha value here, and this, sometimes called the critical value, that's the value to beat. If the test statistic exceeds 7.81, then the p-value will win the day. It will be smaller than 0.05. Now, you can see here, just barely, right? We just barely exceed 7.81. And from the other calculations, we just barely reject the null hypothesis because this p-value is just barely less than 0.05. So in this example, you see one way through any of these perspectives, you see we just barely reject the null hypothesis, but in this case, we do reject the null hypothesis. So to use a chi-squared table online, carefully look for the alpha value that you have to have up here. Typically, it's 0.05. Carefully look for the degrees of freedom. Here, it might be 3 in one problem. It might be 10 in another problem. Find the value to beat, and then compare your test statistic. In this case, I made up a value 8. Compare your test statistic to that value to beat. So that's, in principle, how we use a chi-squared table to resolve these tests. So these are the ways that we run a chi-squared table, if we're a chi-squared test, if we're doing it ourselves. Let's make it practical with a simple example. So our example is going to be, because I'm thinking about home isolation these days, does home isolation change people's interest in film genres? Now, I wish I had time to watch movies. What I did here was I just made up this data. This data, sometimes in this course we have real data. This is not one of those times. This is utterly made up data. I've oversimplified the whole film industry into 5 genres here. I apologize if you prefer surreal or absurdist film because it's not represented here. And then I've made up some data about what people watch normally and what people watch during home isolation. And I made them pretty close. So I'm imagining here, in the back of my head, I'm imagining that maybe Netflix is keeping track. I mean, I'm sure Netflix is keeping track of how people are consuming media, how they normally consume media, how things have changed. And so I'm imagining a small slice of their data set of 1,000 movie views during this time of isolation. So notice that if this is out of 1,000, then the normal expected counts, 30%, 20%, 20%, 20%, and 10%, can be converted to values out of 1,000, 300, 200, 200, 200, and 100. We would just take these as a proportion, 0.3, 0.2, 0.2, and multiply them by 1,000 in order to get the expected counts. So this is basically, this information, these expected counts, these are the CIs from the prior formula. Let's go back to that. They are the CIs, C1, C2 through CK. They are the expected counts. These values are the actual counts. These are the CI hats. Oops. So these values are the actual CI hats here because those are the actually measured counts, which occur in the formula in the numerator here, C1 hat. So the CI hats, those are the actual measured data, and the CIs, those are the anticipated values. So all we have to do is we have to take this formula for the chi-squared test statistic, and we have to plug in everything that we know. So let's go down and do that. So I plug in the CI hats. Here, I plug in these values for the CI hats in that formula. I plug in these values for the CIs, and I get 275 minus 300 squared over 300, and then etc. Notice I have 5 terms here, 1, 2, 3, 4, 5, because I have 5 film genres that are being measured here. The basic question here, and I haven't made a big deal about it yet, the basic question here is there a change in people's interests, or are people's interests basically the same? We're asking, is there any statistically significant deviation from the normal represented in this data? There is some minor variability from the normal, but is it statistically significant? This is what we need the chi-squared test to assess. So anyway, we have 5 categories, and we have 5 terms in this big thing, And we square these all out and divide them and add them all up, and we get 11.2. And if you want to check that, go ahead and do that calculation yourself, but I won't belabor that. So that gives us the test statistic. We don't actually take square root. You might be tempted here, z squared equals 11.2. You might be tempted to take square roots of both sides and calculate what z is, but that's not the appropriate thing. Z squared is the test statistic, and it's that value that we compare against the chi-squared distribution. Now, because we have 5 categories here of film, then we have degrees of freedom 4, always 1 less than the number of categories here. So we have 4 degrees of freedom. So now we need to get the p-value, right? We have the test statistic, we need to get the p-value. And as I said before, there are 3 fundamentally different ways to do that. And we'll go through all of them just because you should be prepared for whatever your situation is, right? If you have to take an exam without a computer, then you might need a chi-squared table. If you're doing this on the computer, you might want to use Colab, or you might want to use an applet or something. So let's do this. Let's calculate the p-value from our test statistic of 11.2 using the function stats.chi2.cdf. So it looks like this. So we plug in our test statistic here, which is 11.2, and we plug in 4 for the number of degrees of freedom because there are 5 categories. This function here will give us a left tail, and we have to remember to subtract from 1 in order to get the right tail. Basically, we're subtracting from 100% to get the other side of the graph. So that gives us the p-value 0.024. That's good news. That's less than the standard threshold of significance 0.05. So that will mean reject the null hypothesis. But let's do the other techniques for getting the p-value before we go on and conclude from this. So this was one technique for getting the p-value. Since I do most of my work within Colab, I find this certainly the easiest way to do it. Let's talk about the second option. We can just follow this applet. If we go into this applet, we need to choose the degrees of freedom appropriate, 4, and we need to choose the right value to plug in for the test statistic, which is this 11.2 value, and we get a p-value of 0.02. Notice that if we calculate the left tail, then we get 0.97, but if we subtract that from 1, we get the right tail, and we get 0.02. So basically, the CDF function is calculating this, and the subtraction from 1 corresponds to flipping it around and asking for the other portion. So this gives us the p-value of 0.024, which is consistent with the p-value that we got here. So that's another perfectly good way to do it. And then the third option is using a paper table lookup. Now, so that you don't have to refer to this, if you have any stats textbook, you should have a chi-squared table in the back. So look in the back of your textbook for a chi-squared table. It might look slightly different from what's here, but let's try to resolve this hypothesis test using the table lookup. So now we need to remember that the degrees of freedom is 4, and our threshold of significance is presumably alpha equals 0.05. So we're going to look up alpha value here, 0.05, and the degrees of freedom here, 4, and we're going to get 9.49. What is that value? That's the critical value, or the value to beat. Our test statistic must exceed this value in order for us to have statistical significance here. Does it? Well, absolutely it does, because our test statistic is 11 and change. So it exceeds 9.5, and so we get statistical significance. Notice that when we do it this way, we don't actually calculate the p-value. We just calculate, oh, I guess it's significant. Whatever it is, it must be less than 0.05. That's what we get from this table. So here, this is the third way of calculating the resolution of the test. So obviously, we don't do it all 3 ways, right? One way or another, we resolve this hypothesis test. We get the p-value, and then we check whether it's less than 0.05. We get the p-value and check whether it's less than 0.05, or we get this test of significance directly, comparing this to 0.05, and the test statistic exceeds this, and that's significance. So one way or another, we conclude here that at the threshold of alpha equals 0.05, we do have significance. We reject the null hypothesis. Now, what does it mean to reject the null hypothesis? In this problem, the null hypothesis is the hypothesis that these isolation views are just normal views. They're just a little different just randomly, but they're normal views. The alternative hypothesis is there's been some sort of change. I don't know what, but some sort of change to this. So, the final conclusion is, by rejecting the null hypothesis, we say the viewing habits have statistically changed in some statistically significant way. Now, notice the ambiguity in that conclusion. That says there is some change. It doesn't say the nature of the change, and that's how the chi-squared test always resolves. It tells you there's something going on, but it doesn't tell you the nature. So you might want to say, oh, well, it's changed. The action watching is less, and the comedy watching is more, and the horror watching is more. You might want to make those conclusions, but those individual conclusions might not be true in a statistically significant way. So we have to be careful. The correct phrasing of the conclusion corresponds to what we actually tested. We tested that there is some difference. The conclusion is there is some difference in the viewing habits. So that's how we perform a chi-squared test in a way, I mean, by hand. Of course, it's not entirely by hand because we've used the computer to do many of the calculations. But that's how the chi-squared works underneath the hood. Now, I want to compare this to the fully automated chi-squared test, which can also happen within the Jupyter Notebook and within Google Colab, or within any Python install that you happen to be using. All we use is the scite-bstats, but instead of using the chi2 function directly, we just use the chi-square, which is the shorthand for, hey, do this hypothesis test for me. Just do everything for me. What ingredients do we need to plug in? We need to plug in the CI hats, and we need to plug in the CIs, right? These are the measured values of, in this case, the views in each category. And these are the expected or predicted values of the views in each category. If you're using this function, you should make sure that the sum of these values agrees with the sum of these values. Otherwise, what are you doing, right? You should expect that it would total to the right thing. So we plug in the actual measured data values here, and we plug in the expected values here, and then this chi-squared function just runs the chi-squared test. And notice it gives us the test statistic, 11.208, but it also gives us the p-value, 0.0243. So if we need either one, then we have them. Typically, once we have the p-value, we don't need the test statistic anymore. So we could just say, okay, the p-value is 0.02. We reject the null hypothesis. So this is the fully automated thing. So you might be asked on homework, you might be asked to do this kind of work, or you might be simply asked to run a chi-squared test, in which case, if you want to use this function, then you can. So one final note here. When is the chi-squared test applicable? If you don't have enough data, then the chi-squared test is probably not a good plan. And if your data is not the right kind of data, then it would probably not be the good plan. So I want to talk to you briefly about conditions for applicability. You need to have enough data so that the expected counts are at least 5, right? In this particular thing, the expected counts were more than 100. If you have so little data that the expected counts are only like 2 or 3, then you can't really trust the chi-squared test to give you the right answer. So you should have enough data that the expected counts are at least 5. The cases should be independent. So in the context of Netflix, this should not like all come from one person, for example. At least, I hope not if it's 1,000 views. But in any event, this should not all come from one person. This should not all come from one time of day. This should be independent data, and there should be no reason to expect that, because one view is an action movie, that the next view will also be an action movie. So these should be independent cases, not affecting or related to one another. So that's what this means. It should be independent cases. The expected counts should be greater than or equal to 5. And the final condition for applicability is the degrees of freedom should be at least 2. If the degrees of freedom is 1, that means that there are really only 2 cases, and you should be doing a simple proportion test instead of going to all the trouble of doing a chi-squared test. So the degrees of freedom should be at most 2. So if you have all 3 of these conditions, independent cases, which is usually the case, expected counts at least 5, which is usually the case, and degrees of freedom at least 2, which is the case if the chi-squared test occurred to you, then the chi-squared test is an appropriate test to resolve the hypothesis.